La référence.
Okay, so good morning to everybody. So this morning we are happy to listen to the lecture by Kirone.
And finish what I said yesterday. So thank you for still being here. This is a reference of the Zia-Schmidtman paper in which they talk about this Kirchhoff formula for how to calculate the steady state probability using graph theory. So it's called Probability Currents as Principal Characteristics of the Statistical Mechanics of Steady States. Very long title. It's in GStatMech 207. It's also in archive. Second thing I wanted to say, yes, yesterday I said something wrong. I answered wrongly to the question that Sanjeev asked me. So if you compute the total charge that has been transferred from one reservoir to another, in this picture, two reservoirs, so you compute the integral of the current over time up to the final time. This is the total charge that has been transferred. You can always take the average over x. It's a finite size system. Well, if you want to compute, even for a system at equilibrium, the large deviation function of this total charge, transport it, it's not a simple task. Capital T, phi of j. So I said wrongly yesterday that this is the chemical potential. I was thinking about the instantaneous current, but if you time integrate it, then of course the statistics of this object will depend on the whole process between 0 and t. And because it depends on the whole process, it will involve different time correlations at different times. So it's not simply a steady state thermodynamic potential. It's more complicated than that. And for example, a very nice calculation was done again by Derrida et al. A long time ago for the symmetric exclusion process, even with equilibrated reservoirs, so reservoirs at the same potential with the same density, and the result is non-trivial. I mean, it's a kind of square root of arcsine law or something like that. It's not something which is simply a free energy or something like that. Okay, so let's continue. Yesterday I argued that large deviation functions are important and so on, and because they, in equilibrium, they in fact can be identified to thermodynamic potentials. Another reason why these large deviation functions are important is because of this Galavotti-Cohen identity, equality, relation, theorem. And again, this is a kind of very general principle. There are many proofs. There are some classic, the first proof by Galavotti and Cohen, I never tried to read it, maybe some of you tried. It's about Anosov systems and hyperbolic dynamical systems. I don't know what it is. But it became accessible, this theory, to the layman, thanks to two major papers, one by Kurchan. I think it's a JStat Phys, but I'm not sure. It's a classic paper in the second half of 90s. Where he proves the Galavotti-Cohen theorem for entropy production for a Langevin equation. And there is another paper which I personally find still nicer, because Kurchan paper is in fact, due to his initial way of thinking, is embedded in a whole kind of quantum mechanical language. He maps the Lagrange Fokker-Planck equation into Hamilton and then uses Hamiltonian language, but there is a nicer paper, I think, for me, at least because it's Markovian and discrete state dynamics by Lebowitz and Spohn, probably the other way around, Lebowitz and Spohn. I think it's 98, and it's in the Journal of Statistical Physics. Yeah. And this is a very nice paper. So more or less the proof I will give here is a kind of, a bit very much inspired from their proof. Okay, so again, what the Galavotti-Cohen theorem says is that under some very general hypothesis that we shall spell out while proving it. The large deviation function associated to an observable R is an almost even function, even up to a linear correction. And the coefficient that appears here has some physical meaning. Okay, so in fact you can say that ultimately the fluctuation theorem of Galotti-Cohen is really spelling out the importance of time reversal invariance in statistical mechanics. It really relies on time reversal invariance. And the beautiful thing is that this is a functional relation, but if you apply it close to equilibrium and just to the first, second order, then you can recover Einstein relation, fluctuation dissipation theorem, and Onsager's reciprocity relations. Yes?
The original paper is really for dynamical systems.
Yes.
And
the later ones are for stochastic systems. So in fact, the difficulty in dynamical systems is that the hypothesis of chaos. You need to prove that something is kind of ergodic and so on. And here it's granted by Perron-Frobenius, if you wish. Yeah. So a large part of the technical thing, which you have to prove that somehow you cover the whole phase space, here it's given somehow. Okay, so let's do a very simple proof in the case of Markovian systems. So one way of stating it is going back to detail balance. So I told you yesterday that one of the main discoveries of Onsager was that time reversal is related to detail balance. It's even equivalent. And this is a major property of systems at thermodynamic equilibrium. So I just recall it. If we just spell out detail balance for the canonical measure, it just means that this relation is satisfied. And it means that if you could go from C to C prime from the state C, which has probability exponential minus beta energy of C divided by Z, it is equal to the opposite weighted rate of going from C prime to C. Of course, we can rewrite it by just transferring this thing here and reinterpret this detail balance relation by taking into account energy transfer. So if we go from C to C prime by transferring the energy delta E, the rate of doing that is equal to the rate of going from C prime to C by transferring minus delta E, but multiplied by this factor exponential minus beta delta E. This is nothing but detail balance, just rewritten with different notations. Okay, here this index delta E, which did not appear here, has been just added ad hocly, in an ad hoc manner, to keep track of the energy exchanges. So that's just like that. Okay, now the main point is the following. Non-equilibrium is defined as detail balance breaking. It's really the same thing. Time reversal invariance, which is broken. But, and I think this is one of the key insights that these people had in the 90s, although you break, yes?
Is there something microscopic time reversibility and macroscopic time reversibility?
So somehow I will come to that. Exactly. That's exactly the point. I mean, maybe stated in another manner.
So when you say time reversibility, it's macroscopic, is it?
Microscopic.
What do you mean microscopic?
Microscopic. So that's the main point. I mean, when you go from micro to macro, okay, you can, by tracing out some degrees of freedom, you can lose apparently time reversal invariance. But microscopically, you have it. So now suppose I'm a mathematician, I write a Markov process. The Markov process has absolutely no reason to satisfy detail balance. It's a Markov process. Who cares? But now if you write a Markov process that comes from physics, we know that ultimately the microscopic laws of physics are time reversal invariant, forgetting about weak interaction. Huh? So microscopic laws of physics are time reversal invariant. So somehow, some taste of this time reversal microscopic invariance has to remain hidden into your Markov process if the thing is physically sound. Otherwise, it's just a mathematical game. Okay. So that's the main point. Even though detailed balance can be broken in a system like that, if the two reservoirs are not at the same temperature, ultimately, if you write the big Hamiltonian that describes absolutely everything, including the reservoirs, this Hamiltonian is time reversal invariant. Hamiltonian dynamics, Schrödinger dynamics is time reversal invariant. So even though by tracing out on the degrees of liberty of the reservoirs, even though you get something which naively is not time reversal invariant, something of this initial time reversal invariance has to remain hidden. And if you dig out this thing, then you get generalized detailed balance, and you can prove Galavotti-Cohen theorem. That's the philosophy behind it. So, in fact, there is a natural way of breaking detailed balance. Out of equilibrium, detailed balance is broken, but it's not broken in a totally arbitrary way. It's not broken in a blind way. It's broken in an educated way. So that's the whole point. Thanks for the question. So now suppose that we are in the non-equilibrium case. We have two reservoirs and a system which connects them, two reservoirs at different temperatures, T1 and T2. And now suppose that during an elementary step of the process, the system can exchange energy or matter or particles either with the first reservoirs that we call delta E1, this exchange, or with the second reservoir, delta E2. And there will be a kind of local detailed balance. So detailed balance can be generalized as follows. So now we keep track of the two indices, which represents the exchange between the first and the second reservoir. And instead of having only one temperature and one energy exchange here, we shall have both temperatures, beta 1 and beta 2, and the two energy exchanges which are possible with the two reservoirs. So for the moment being, I have not proven that relation. I'm going to give you an argument, not a proof, but an argument that justifies it, that I learned from Derrida and Derrida's lectures. There's a nice review paper by Derrida, also in 2007, maybe in the same, it's in the same journal, maybe even the same issue, but it's on the web anyway. And the Newton Institute lectures, exactly. So this is the whole point. Even if you have a system which is out of equilibrium in contact like 2 or 3 or 4, then you have to put 3, 4 temperatures, reservoirs at different temperatures or different chemical potentials, then you will have mu1, mu2, delta n1, delta n2. Detailed balance is broken, but this relation has to be true. So how do you prove such a relation? How do you argue that such a relation is true? Well, again, the same trick. If we consider now the global system plus reservoirs, then we have an isolated system which is governed by Hamiltonian time reversible dynamics. So the global system has no choice. It has to satisfy detailed balance. No choice. Globally, the thing is time reversal invariant. So now if we count the rates not only for transition at the local system C and C prime, but we add the states of the reservoirs, and the states of the reservoirs are just given by their energies or their total number of particles. We don't know anything else about the reservoirs. We're not interested in the velocities in the reservoirs or something like that. Then we have the fact that these global rates, they have to satisfy a real detailed balance relation. So that's a way of arguing it, okay? In fact, if you remember your basic lectures in statistical physics, in equilibrium statistical physics, this is the way one deduces from equipartition in the microcanonical ensemble the Boltzmann law in the canonical ensemble. You add the reservoir of temperature, you apply microcanonical law to the global thing, and then you trace out over the degrees of freedom of the reservoir, and you get exponential minus E over KT. So that's exactly what we are doing here. We are writing a detailed balance relation by putting the microcanonical measure on the global level. And of course, we use Boltzmann relation, Boltzmann formula. And because the exchanges are small, E primes and E's differ little, when I transfer these things here, I can make a first order expansion of the entropy. use the fact that the derivative of the entropy with respect to the energy is one of the temperature, and I get this relation. So I argue that, I agree that there can be many, this is not a proof. And it's not a mathematical proof. This is just a kind of physics argument, but I personally find it quite plausible and convincing.
How mathematicians would prove it? I mean, is it just rendering this more rigorous, or do I already find it quite convincing and almost rigorous?
Me too, but I don't know. You know, they always find things that we consider.
That's not the way at all. The mathematical proof is completely orthogonal to this one.
I don't think there is any mathematical proof, in fact. Yeah, and no, I don't think so. But what happens is that if you look at good Markov processes that do represent, for example, dynamics of molecular motors and so on, they always have this kind of property hidden somewhere. Okay. So now you see we just have somehow what do we have to do? We have to redo Onsager's proof that we did yesterday, but using generalized detail balance. So keeping track of the exchanges with the two reservoirs and being slightly more careful. That's all. So we'll do it. Merci. It's not my proof. Okay, so now let's be a bit more pedantic and slightly more abstract. So instead of energy exchanges, because I will be interested in the ASEP and so on, let's talk that when you go from one configuration to another, some quantity y is incremented by small y. Okay, before it was the energy, delta E1, delta E2, but some quantity changes by small y. And I keep track of the increment as an index of the Markov rate. Okay. And we also suppose that if we reverse time, if we go backwards, then the same quantity, capital Y, suppose it's the total charge transmitted, is decremented by small y. So, okay, by time reversal, the sign changes here. And suppose that we have a kind of generalized detail balance of this type. So I'm just really spelling out this thing. In one special case, I'm just taking track of the exchanges of the left reservoir, forgetting about the other one, and I suppose that I have such a relation that I call generalized detail balance. Okay?
Like in the statistical mechanics, when you go from this, you have this microcanonic thing. So you assume that it's ergodic, like all states are equally like there, right?
Yeah.
Basically, it's equilibrated.
Yes.
But now you have one bath at very high
one
temperature
temperature
and one bath at very low temperature.
Yes.
And now you connected them.
Yes.
So you have the whole system, but is it ergodic now?
So again, this is a mathematical question. I have no idea. In fact, it depends. You have to prove it. But the thing is that if you connect them, ultimately they will reach a final temperature.
But that's
far away.
Far away.
Yes.
But like that, when we are measuring this, they still have to differ.
Of course. So there are many time scales, but we suppose that the rates of transition for the whole system, for the global system, are such that in the end, the global system will attain thermodynamic equilibrium for the global system.
And you're saying that the rates should not be time dependent?
Yes. I mean, T1 and T2, yes, here I suppose that the rates are not time dependent, but T1 and T2 are just an initial condition. But in the end, it will reach T1 plus T2 over 2, or whatever. Okay. And this global system is described by a Markov process that converges to thermodynamic equilibrium and that satisfies detail balance. And now if I trace out the degrees of freedom of the two reservoirs from this global system, I should obtain my restraint Markov model at the level of my small rod. That's the assumption behind it.
But in this rates now, the temperatures are still okay.
So no, the temperature are just here. They are not in the rates.
Oh, okay.
It's just as if I have a system, forget about the two reservoirs, which goes to thermodynamic equilibrium and which I prepare in a bizarre way. I have one box of gas and I prepare it by putting things only on the left.
So you're saying that the dynamics is equilibrium, but I can
Yes.
start with a
As a very non-equilibrium.
Okay.
Okay. In fact, what we are doing here is a kind of intermediate asymptotic, if you know this Barenblatt classification, because somehow we know that in the end it will reach real equilibrium, but we are considering an intermediate time where the two reservoirs are not depleted and the system itself, the intermediate system, has reached a stationary state. So this should be an intermediate asymptotic for these rates. Not the real steady state, which is equilibrium, but a kind of intermediate state. Okay, so we suppose that we have this relation, and now we apply the same game. So we do the same thing. We consider a trajectory, which goes from C0 to Cn with discrete jumps. But now what we have to take care of is that each time we have a jump, some quantity y, small y, is added to the big Y. There is some increment. Okay, so I did it. I didn't do it in details, but you can really do it. It's quite easy. I mean, it's just exactly the same calculation as before. If you just take the ratio between the probability of a trajectory and the time reverse trajectory, so you don't have detailed balance anymore. So the initial and final stationary measure of C0 and Cn will remain. The same simplifications will occur thanks to this relation, but you will have to keep track of little y1, y2, yn. Okay, just redo the calculation. It's really the same as we did yesterday here. I'm not cheating. It's really the same, but you just have to take care of this small y. And so instead of you'll get this thing again, but now you cannot simplify it by using the zipping procedure. You have to use the generalized detailed balance relation. So you will have this exponential gamma y1, gamma y2, and so on appearing in these ratios. This ratio is not equal to 1 anymore, but it's exponential gamma y. So of course you will have a global exponential gamma y1 plus y2 plus yn that will appear, which is total y, okay? The total charge, or the total quantity transferred when the system follows the trajectory C of t. And also remember that because of time reversal, C of y of c hat is minus y. So now that we have this relation, we have Galavoti-Cohen, essentially Galavoti-Cohen's identity. So there's some little tricks now. You see, this thing is a bit annoying. So if we take the log and put it into the exponential after dividing by gamma 0, we just redefine, instead of y, this capital Z, just putting the thing into the log, and so on. And the relation before can be rewritten like that, in a compact way. Okay. P of C divided by P of C hat is exponential gamma Z0. But now I can just transfer this denominator to the right and add an exponential gamma Z on both sides. So this relation is exactly equal to this relation. See, I just transfer this thing to the left, this thing to the right, and I just add a factor, exponential gamma Z, on both sides. Simple algebra. Now so gamma is this factor that appears in the generalized detailed balance. Here it's an arbitrary one, but if you remember the previous identity, it was 1 over kt.
So that's gamma naught.
Yes, maybe I forgot to go. No, there's gamma naught here, okay? Gamma naught is here.
Yep.
Gamma naught is here. And I just multiply by this exponential gamma z on both sides. I'm allowed to do that, okay? And now I remember that z is odd with respect to hat. So exponential gamma z is exponential minus gamma z of c hat. Okay, so now I have this relation. Trajectory per trajectory. This equal to this. Yes?
So that assumes that you have a stationary distribution.
Yes, so you assume that you have a stationary distribution, and you also have to assume that this thing is non-zero.
Yeah.
So there are counterexamples. There's a nice series of papers by Schutz, Rakos, and this young lady, Rosemary Harris, in which they study ZRP, and in which, in fact, you have condensation. So some rates become zero, this thing blows up, and Galavotti-Cohen is not true. So here, at each point, at each assumption, you can find a counterexample and kill it. Okay. So there are assumptions here.
So with the two reservoirs, there was a beta 1 and a beta 2.
Yes.
So what is gamma or not? Is it? It's not just delta beta.
No, so there will be two betas. So I will.
So gamma naught is in general like many.
Yes, you have many observables. And probably I have a transparency which tells that. But just to simplify, I took only one, not to to carry over two variables and so on. Otherwise, you will have gamma 1 Z1, gamma 2 Z2, gamma 3 Z3, and so on. It was just to simplify notations. But
Why
yeah.
should that be stationary?
Uh,
Even if that is not stationary, you will still be able to define that.
Yes, but what I'm doing here is I'm computing the probability of a trajectory in the stationary state. Okay. Otherwise, you see, if I take a trajectory, I have to wait with the initial condition. So this will be p at time t0. But then the final guy will be p at time tn. You see, if you remember, okay, all these details are important, but then when I have to go into the proof again and again and learn it and see what, you see, this is the basic proof. So now if I do it in a non-stationary thing, I will have to put p at time t0 here, okay? And then when I time reverse, here, p at time t0. And then when I time reverse it here, I will have p at time t0 at Cn. But they are not the same now, t0 and, I mean, when I reverse it, I will finish at, with probability, I will finish at configuration C0 at time capital T. And don't forget one important thing, is that detail balance in the case of Onsager is a property of the stationary, of the equilibrium measure. So if I do it in a non-stationary context, I will not be able to use that anymore. And I'm stuck. Okay. So one has to be careful with all these details. So there are some extensions in very special cases to non-stationary, Galavotti-Cohen and so on, but usually it's a property of the stationary state.
Then these probability functions will not be same. Basically.
They will not be the same, yeah. Well, look, even if you take a system which goes at thermodynamic equilibrium, we very well know that it's not time reversible. If you start from a non-equilibrium state, even in a system which satisfies detail balance, okay, which ultimately will reach Boltzmann state, but of course the evolution is not time reversible. I mean, if you put water at 0 degree and heat it, it will go to 20 degrees or 50 degrees, so it's not at equilibrium. I mean, okay. So it's really, here we are constructing the path measure in the steady state. Okay. So let's go back. Okay, so now we have this. So now we just have a pathwise identity for this quantity exponential z, but this is nothing but a generating function. And this one. And now we just sum over all configurations, all possible histories between time 0 and t. So we just sum this quantity and use this relation to rewrite this term as exponential minus gamma z of c hat, probability of c hat. Now there's a very little trick. Summing over c is the same as summing over c hat because there's a duality. So I'm not losing anything here. There's no Jacobian, if you wish. And what is this equality? It just tells you that the exponential generating function of gamma minus gamma 0 z is equal to the exponential generating function exponential minus gamma z. And this is Galavotti-Cohen. This is nothing but Galavotti-Cohen at the level of generating functions. Okay? So let's go now back to large deviation functions. So yesterday I didn't say it in a very clear way, but just believe me, redo it or use the notes to redo it. There is a relation between the exponential generating function here and the large deviation function phi, they are just Legendre transform of each other. This can be proved. This is proved here in one line. Okay. I don't go into the details. This is just very simple. Okay, so once I have this relation, I can spell it out at the level of exponential generating functions, but also large deviation functions. First of all, so this is again another assumption which does not hold in complete generality. There are some assumptions, but usually these quantities z and t, yt grow with time linearly, and their difference here, this thing, remains bounded, which means that it's an irrelevant additive factor. It's not always true. As I told you, Schutz et al. Had an example in which this is not true. But if this thing remains bounded and these two things grow linearly, it means that in the long time limit, the two statistics are the same. So what we can write is that this is exactly true for z. If this is bounded, you can prove that this is in the large time limit true for y also. Okay. Now, because they grow linearly in time, you can prove using Laplace transforms that this exponential generating function behaves in the long time limit as the exponential of the cumulant generating function, e twiddle of gamma times t. There are plenty of small things to be put into but the details are given in the previous transparencies. Okay, so this identity, if you just write this thing here, tells you that this cumulant generating function satisfies the Galavotti-Cohen identity. E of gamma minus gamma 0 is equal to E of minus gamma. So just to maybe summarize the proof, there is a generalized detailed balance. We redo Onsager's calculation of taking the ratio between forward and backward trajectories, but instead of getting 1, as in the case of Onsager, we get somehow the asymmetry of the time evolution of the system is really related to the current, to the total current of y that has been transported. And this is the case. I mean, the reason we see that things are not reversible is because of these currents. Things go in one direction and not the other one. And now using this nice identity, you can easily prove that the exponential generating function of y satisfies this nice relation, which in fact tells you that the Laplace transform of the probability of y has a symmetry around gamma 0 over 2. Because this is nothing but the Laplace transform of the probability distribution. So this Laplace transform evaluated at gamma minus gamma 0 is equal to the Laplace transform at minus gamma. Okay? And this is one version of the Galavotti-Cohen relation. But now there is a nice identity relation between this and large deviation functions. It's a Legendre transform. So instead of writing this relation, if you spell it out for the Legendre transform, you get the Galavotti-Cohen relation. Okay, that's quite simple. Yes.
Gamma naught, I understand its meaning. But gamma, it looks like you have introduced it in a bit artificial way.
Yes, because I want to find a relation for the Laplace transform. So it's true for any gamma. Yeah. The other gamma is just, well, I want somehow
when you
to
have done this trick there.
Yeah, I want to spell out this relation.
Right.
And I see that this relation is nothing, is this one. If there are? So if there are more gammas? Yeah, so probably this will come here. Now we have more gammas, that was your question. So if you have more gammas, we have more quantities which are transferred, which I call y1, y2, yk. And then we have a generalized Galavotti-Cohen relation, either at the level of Laplace transform or at the level of large deviation functions. So in fact, this large deviation function is even with respect to all its arguments up to a linear term. I mean, simultaneously, you have to change all the signs.
This relation is always true, right? Even if some cases that red relation is not true. The, no, second
This one?
second
The
one is probably
second
always true.
one, yeah.
I mean, in like some cases,
Well, you have always this stupid term that has to remain bounded.
but that one probably doesn't contribute to the eigenvalue, no?
Well, this relation is always true for the z variable.
Yeah.
Okay. But then you have to go from z to y, and this can spoil your thing if you have condensation, typically.
I go to your next slide.
Yes?
Yeah.
So here you see, I assume that this relation, which is completely true for z, is also true for y. So I somehow have thrown out this boundary term.
And you think that the boundary term can contribute to this epsilon?
This boundary term can make a major difference between the statistics of y and the statistics of z. In the case of z,
So that I agree.
yes,
But I'm saying when you write down this way,
this is okay.
no, that go to the next one.
Yes.
So when I go there, you're saying that it might contribute to the eigen. This is the eigenvalue, right? Probably epsilon. No, next one.
Okay, so first of all, I have to
next
use.
one.
So next one, this may be true. This, okay, suppose this is true. But how can I plug it back if this is not true? I'm using both this and this to get this. You see? So even if this is true, and this is very true in general, this is a dominant eigenvalue, but this is in fact Galavoti-Cohen. This has nothing to do with Galavoti-Cohen. This is just the existence of a gap, if you want, this is Perron-Frobenius, essentially. Okay? But this is Galavoti-Cohen. This is a non-trivial thing. And the problem is that I have to go from z to y. So in 99.9% of the cases, it is true. But in case that this boundary term itself becomes unbounded, it can be spoiled. But this is a detail, in fact, it's not so important. But because Gunther, wrote a paper
So
and
this expectation value when you take,
yes,
so you basically take over the initial condition and the trajectory, right?
yes,
But if I leave the initial condition out of this average,
yes. Okay, maybe.
so then this is probably true, right?
Yes, but you have also to let the final thing, because you see, final and initial,
So if
when
I
you
just-
reverse
so
the,
if I just leave this final and initial,
okay, maybe.
so then it's true. So
maybe.
then the original process should have the same eigenvalue. Only the wave function should depend on
Yeah.
that these two averages.
Yeah, you're telling me that if you quench the initial condition
Exactly.
and the final condition, that this is a number,
That's a number.
25.
Yeah.
And then, of course, y and z have the same statistics, but this is a bit artificial,
No, but
isn't
then
it?
what I'm saying is that I'm saying something more than that.
Okay.
So I'm saying that if I look at your equation, so that
Yeah.
should have the same eigenvalue as this epsilon.
Yes.
So now, in like averaging over this the initial condition and final condition
Yeah.
should only contribute to the wave function, because that doesn't depend on the part. It's just some
Okay, I agree.
right.
But the problem is that you're right. But the problem is that probably the prefactor will blow up.
Yeah, exactly.
Yeah.
So, but then
Things
I'm
that you
saying
computed, yeah.
Exactly. So then
Yeah.
I'm saying that at the level of the eigenvalue,
This may be true.
this is probably always true, right?
Okay, maybe.
If I just think Galavoti-Cohen at the
Maybe.
level of the eigenvalue, that's probably
Okay,
true.
but maybe you cannot go from here to here.
You cannot
anymore.
go from here to
Yeah,
here.
maybe. I didn't look into the details. You're probably true, yeah.
Right?
It's really the projection into the dominant wave function,
Exactly.
which will give an infinite factor
Exactly.
here, and then, yeah, then you lose the relation between epsilon and
then
phi.
Yeah.
Yeah, probably. Yeah. But in fact, personally, in all the cases I know, these things are perfectly bounded and
No, it's
Like that.
for like if you have a Brownian particle, this problem treated like this correct.
yes,
Brownian particle connected to heat box. It's not
Yes,
true.
it's not
there
true.
also this unbounded phase.
okay,
So then,
Okay.
so in heat conduction, in most cases, probably it's not true.
okay. And then do you have Galavoti-Cohen?
It's violated.
It's
At the
valuative.
level of
Yeah.
the eigenvalue you
Yeah.
have,
At the level of the eigenvalue.
But not this
not
prefactor.
because the
Okay.
wave function.
Yeah. Okay. For the reason that this thing is not bounded.
Yeah, exactly.
I think whenever it's unbounded,
Then it's something wrong goes on. Yeah, exactly. So it's very important that things remain bounded. And the case I have in mind is these exclusion processes, in which case this is a number of number one.
Yeah.
And it's okay. I mean, they differ essentially by the number of particles remaining in the system, but the system is of finite size, and so on. Okay, so I think, yeah, that's very useful. Okay, I'm just looking at the time. Oof. Okay, wow. But it's good that we discuss. I think that's more interesting. What I'm going to do. Okay. Leibowitz and Spohn proved their theorem. They applied it to a very nice quantity, which is the. It's just a remark, but it's cute, I think, which is the entropy production. So again, I think maybe it's probably Udo who defined that later as a path entropy trajectory. Path trajectory. Bref, entropy of paths. If you do an elementary step in a Markov process, you can define the generation of entropy as the ratio, the log of the ratio of the two rates. Okay? And now the nice thing is that if you look at this quantity, delta sigma, then the detail balance, the generalized detail balance, is trivially satisfied with gamma 0 equal to 1. Just, it's a kind of stupid identity. It's 1 equal to 1. So you can apply the whole procedure to this entropy generated through a path. And in fact, indeed, the large deviation function of the entropy generated by the process satisfies the Galavoti-Cohen relation with gamma 0 equal to 1. So it's kind of, how do you say, automatic thing, but it's nice. Okay, I wanted to tell you a bit of some applications of that to molecular motors, but I'm not going to tell you about that. But if you have a molecular motor, you see the molecular motor eats some ATP, so it consumes chemical energy and transforms it into motion. So you have two currents into the system. You have a chemical current, which is depletion of ATP into ADP plus P, and you have a mechanical current, which is transport of a cargo. So you have two variables and two types of exchanges, steps taken by the motor, like a random walker, but also this discrete reaction. I mean, ATP molecules are eaten one by one. So you have two numbers. You have two physical quantities, which are the position and displacement of the motor and the total ATP consumption. So you can play the same game, define generating function, cumulant generating function for the total displacement and the total number of ATP consumed by your motor. And everything is satisfied, this Galavoti-Cohen theorem is satisfied, and so on and so on. And I think this is a very nice example that we worked out a few years ago with people in this SPCE, where you can really show that from the Galavoti-Cohen relation, which is very easily satisfied and proven here, there's no problem with infinities and things like that. It's a finite state system, and so on. You can really prove that these relations imply Einstein relation between, Onsager relation. So maybe, no, I'm going too fast, sorry. Let's spell it out maybe slightly more. I will take a few more minutes and talk less about the exclusion process. So let's do it again. So now we have this molecular motor, which proceeds at a certain speed and which consumes ATP at a certain rate. So you have two currents, the current, the speed of the motor, and the rate consumption of ATP. And we are interested in computing these two currents as a function of the external load and the chemical potential of the reaction between ATP and ADP plus P. So there is a load and there's a chemical potential here. Okay, so the thing is that if we apply a little force, if we apply no force, there is no cargo, there's nothing attached to the molecular motor, and we suppose that ATP and ADP plus P are at equilibrium in your cell, then there is no motion. Everything is at equilibrium, and then the two rates, v, the speed of the molecule, the motor, and the rate of consumption of ATP, both of them vanish. Now suppose that we put a small force on the motor, and we put a small unbalance between ATP and ADP. So now there is a reaction going on, some consumption, and the motor will start to move with a speed v, and there will be some consumption of ATP. If everything is small, we can make a linear response theory, and we'll have 4 Onsager type coefficients. We have a matrix L, which couples the external drives with the responses. Okay? And these are the linear response coefficients. So at the level of linear response theory, we have Einstein relations. We know that the diagonal terms are equal to the equilibrium fluctuations. And we know, because of Onsager, that the off-diagonal terms are just equal. This is classic old linear response theory. Now suppose that we are far from equilibrium. How can we look more generally to this problem? Well, we have learned from Galavotti-Cohen that for the whole procedures, that we have to consider rather the exponential generating function of these two quantities. And thanks to all that what I said before, this exponential generating function satisfies the Galavotti-Cohen relation. That's what we know. Okay? And we also know that if you want to compute the speed, the velocity of the molecular motor, we have to take the derivative of this generating function with respect to gamma. Because if we take the derivative with respect to gamma and take then gamma lambda equal to 0, we shall have the average value of x. If we divide by t, this gives us the speed. So here the t is here, in fact. Similarly, if we want to have the average consumption rate of ATP, we have to take the derivative with respect to lambda. And then put lambda and gamma equal to 0. So if we do that and use the Galavotti-Cohen relation, we find that the derivatives at 0, 0, they're exactly the same thing as the derivative at minus f external and minus delta mu. This is Galavotti-Cohen. So this is just the Galavotti-Cohen relation at first order. This is a general Galavotti-Cohen relation, and now I just take the derivative of this relation at gamma equal to lambda equal to 0. This gives me a relation between the speed and some derivative of this epsilon, but at a different point. Okay? Why not? And this is true whatever the values of F exterior and whatever the value of the unbalance of concentrations between ATP and ADP in my cell. Now suppose that we are close to equilibrium. So we suppose that the load and the unbalance in the chemical reaction is small. So now I can take a first order expansion of this relation, close to equilibrium. So if I do that, I get this. Okay? I have already one derivative here. So now I take another derivative because I take a linear expansion. So these two relations, they become equal to that. Yes? And now there is a miracle because now I'm close to equilibrium, but I'm doing nothing but linear response. And see what happens. The off-diagonal terms, they have to be equal because they're just second derivatives with respect to lambda and mu. So Onsager relation is nothing but Schwarz identity. ddx, ddy is ddy, ddx. Comes from nothing.
This ADP transition is just a two-state.
Yes,
and
yes.
Is the total number of down
ADP that I, yes,
down to up to.
down to up to down. Yeah. How many I've eaten, how many ATP I have consumed. Exactly. So this is very, very simple. It's just an illustration of the whole thing. So you get Onsager relation just because of second derivative equality. And now what is Einstein relation? Well, this term here is a second derivative of this epsilon. But what is the second derivative of epsilon? Let's go back to the definition. The second derivative is nothing but x squared. So it's fluctuation at equilibrium. So we get the fluctuation dissipation relation just by identifying this term to the fact that this is nothing but diffusion constant. So, okay, I went a bit maybe too fast. Sorry if it's the case, but just to, I mean, this is not a big highbrow physics. I mean, this has been around for the last 10, 15 years. But if you apply Galotti-Cohen to this very simple two-state model coupled with a random walker, the motor is a random walker, and this is a two-state model between ATP and ADP, okay? And just spell out the whole procedure, you will see that you get much more than linear response. And linear response is a simple consequence of Galotti-Cohen. Okay? So here the randomness is purely on the motor? And the other thing also, both of them. Yes. So yes, but the motor can also somehow, if it goes backward, it can make the reaction run backward too. No, you could also, I mean, in fact, there is a whole phase diagram, and there are some stages in which the motor, instead of doing work, is extracting work from the system and creating ATP from ADP. It's not very natural, but it could happen in certain. You see here, for example, in region B and D. Okay, mechanical work is converted into chemical energy. So somehow mechanical work of the motor is used to, to store ATP, which is not the normal thing. The normal thing is to convert chemical energy into mechanical work. Okay, so I will not talk about Dzerzhinsky. I prefer to talk a little about the exclusion process. If I'm able to change that, escape, close. Okay, so let's go, very rapidly, because of course I'm very late. I wanted just to tell you about some things about the exclusion process. I'm going to be quite sketchy. There were some details about Bethe-Ansatz calculations, but I just have no time to tell you about. So I think the message I want to tell you in the second part is that the exclusion process has been studied a lot, including by many people in this room. And you may think that why so many calculations, so many different techniques? And I really want to contrast the fact that if you take different boundary conditions, the techniques are quite different, and the results are quite different. In fact, you can almost say that there are different words inside this exclusion process, and even different equipes, and people work in different regions of this model, and the techniques are not easy to connect. So let's see what's in more details. So okay, I'm not going to tell you about it. Comes from biology, as I told you the other day. These people really invented it. And then even nowadays, for example, if you're interested in modern applications of the exclusion process to biophysical problems, there are very nice series of work by Frey. He's still working on these exclusion models. People are really generalizing it. You can have particles hopping and disappearing and sedimenting in the bulk. You can have even models in which the size of the lattice is not fixed. You can have one more, it's a kind of fungi or some microtubule which is growing. It's really, there are plenty of things that has been done. You can have slow and fast jumps which somehow modelize blockage along the RNA. People like Tom Shu, who's in UCLA, has really used finite size exclusion processes and so you see the basic exclusion process in which you put no disorder, you just make it pristine, you can make calculations. But then it becomes remotely related to reality. If you want to use it as a modeling, as a serious tool to model real stuff, then you need to put disorder, unequal rates, absorption and evaporation, and then there is no hope to do exact calculations. Either you field or you put it in the computer, but then you can compare with real things. For example, Tom Shu, he has a very nice web page and he's very active. He has really played this game, that you don't try to solve things exactly, but you add as many ingredients as necessary to compare it with real things. And it works quite well. So this is, of course, totally orthogonal to my point of view, but it's useful. And it's important to know that people are doing serious work and non-trivial work in this direction. Okay? And of course, nice relation with KPZ, which is somehow the most dear to all of us. I mean, ASEP in our community is important because it's a discrete version of KPZ. And the thing I wanted to tell you that is whether you consider, if you consider ASEP on a ring, closed ring with asymmetric jumps, or on an infinite system, or a finite system with reservoirs, all these three problems, although they all talk about ASEP, they are very different and they require extremely different techniques to be studied. Okay? So let's start, for example, with the simplest case, which is the finite system with periodic, so no reservoirs. Okay? This system can be mapped to a spin chain, to a Heisenberg non-remission version of the Heisenberg spin chain. And then the technique to solve this kind of systems, the best technique is the coordinate Bethe-ansatz. With Bethe-ansatz, you can obtain many results. So let's suppose that we are now on a ring. We can write the Markov equation of this system, and a configuration is just denoted by the position of the n particles. Okay? So you have a nice kind of discrete Laplace equation, which is true for this system. You have only to be very careful that it's not a purely Laplace equation. When particles are next to each other, some jumps are forbidden. But now the miracle, which was first very easy thing that I leave you as an exercise, is that the steady state of this model is uniform. All configurations occur with same probability. So x is the position of the particles. Oh, sorry. So this is, this is a q. Yeah, sometimes I call it x, the backward jump. Yeah, that's a mistake. It will probably occur again and again. So all the configurations are equiprobable. And now the first very big insight, I think due to Deepak Dar in the end of 80s, was that this model is nothing. The Markov matrix of this model can be rewritten using Pauli operators as a spin chain. So this was a 2 lines remark by Deepak, which was then really implemented and understood and used by Gua and Spohn in the early 90s. And because it's a spin chain, you can use all the tools that have been developed for 90 years now to study spin chains. Okay? And the basic tool to study a spin chain from an analytic point of view is the Bethe-ansatz. So here, because we are on the closed ring, I put the x here, so it's really periodic. If I want to transform it into an xxz, then I will have twist. Yeah. So here I let the x here. Yeah. You're right. The usual thing is to go into a xxz spin chain, so somehow remove this x factor, this asymmetry factor, by making local rotations. But then there's a twist between the first and the last site.
And the last term is just an overall.
Sorry?
The last term is just an overall constant.
Oh yes, this is just a number. L times this, yes. But this is an exact mapping. Absolutely no approximation. Okay? It's very easy, in fact, but it's very important. Okay, now spin chains. I'm not going to give another lecture on Bethe-ansatz. I came a year and a half ago and took 6 hours for that. But the trick is that you have Bethe-ansatz, which means that you can write the wave functions of this spin chain as a linear combination of plane waves, and you can compute the energies and the plane wave momenta by solving nonlinear polynomial equations. Okay? nonlinear algebraic equations. Okay, this seems to be a difficult, complicated task, but it is doable because these momenta have some nice geometric properties and so on and so on. And one big thing that was done in the 90s is that you can compute the gap of the system, which tells you about the relaxation time, and you can even find some imaginary contribution to this gap, which are in fact oscillations. And the first people who really did it were Gua and Spohn, after this 4-line paper of Deepak, who never published his calculations, but people know that he was the first one to do it and to compute this 3/2 exponent in his notebook, so this dynamical exponent. And then there were many other works by Kim, Satya, Mustansir, Paul, Krapivsky, De Geer, Ressler, and so on and so on. So main tool, coordinate patterns. Okay, I have unfortunately no time for that, but you can ask yourself another question about the current. Suppose I sit here and I want to compute how many particles went through this bond, positively if they go in the positive direction and negatively if they go in that direction. So what is the total integrated current through this bond between time 0 and t? And then again, thanks to the same techniques, you can compute the generating function of the cumulants of this quantity, of this current, y of t. You can compute this generating function again using better ansatz. So this is one very important insight. And the first people who got this insight were Derrida and Leibowitz 15 years ago, 17 years ago. They were able to compute the cumulant generating function of this total integrated current as a parametric series. So they didn't get E of mu, it's not possible usually, but you can get it E as a function of a parameter B, mu as a function of parameter B, and eliminate B order by order into these two series.
They did it using the better ansatz?
Yes, yes, they did it using better ansatz. So they did it for the totally asymmetric exclusion process, because in that case, the better equations, in fact, decouple. You have n momenta, n particles and n momenta in the better equations in general, which are totally coupled. Here are the better equations. But when x is equal to 0, which is the ASEP case, there is a nice decoupling property. All these products go away and things decouple, and you can do things. So then it took a long time to be able to do the things in the general X case. If the equations are really coupled, how do you solve it? And this was done by Sylvain during his PhD, Sylvain Prolac, and then it's possible to do things, but unfortunately I really don't have the time to tell you about the details. But the physics here lies in the following. You can deduce from this generating function the large deviation function. You can plot it, and you can get the asymptotics. So this is not Tracy-Widom because we are on a finite system, but you can calculate things, the tails and the quadratic behavior, and so on and so on. So the important physical thing to notice is that the distribution of this current, so again you have a typical current, which is the steady state current, but you can ask yourself the question, what is the probability of getting more or less? Well, it's easier to get less than to get more. And this is quite trivial to understand. If you have your exclusion process, to get less current than the typical current, you just have to slow down one particle, which blocks all the others. Okay? But if you want to get more current, you have to accelerate all the particles. And this is very unlikely. So that's why the large deviation function is much more steep in the positive direction rather than in the negative direction. And the power laws are not the same. 3/2 here, 5/2 here. This comes from this physical. So it is related to the height distribution in KPZ if you consider only KPZ on a finite ring. Yeah, but if you now consider the calculations that Tomohiro has done, it's on the infinite line. And in fact, there are very recent very, very recent results of Sylvain Prolac, who has been able to find the crossover, going to the finite ring.
Then you
to
should
the,
get this tracy between.
then, in fact, he finds the limiting tracy Widom from this thing. It's an extremely non-trivial calculation.
Is this last paper? No.
Yes, yes, he just put it on archive 2 weeks ago, maybe, yeah. So using these techniques, you can calculate moments, first moment, second moment, third moment, and you can even, in the weakly asymptotic limit, get the full series, okay, and get Gaussian and non-Gaussian fluctuations. One important insight I want to show you is that if you plot the large deviation function, now the large deviation function in the weakly asymmetric case, you see that if asymmetry is big enough, there is a kink developing into the system. So the large deviation function becomes non-analytical for large enough asymmetry when the current vanishes. And this is a sign of a phase transition into the system. This is, in fact, if you look at what happens physically to the particles, here a shock appears into the system. Okay? So there's a whole story. I mean, each of these things, of course, could be spelled out, and could take half an hour telling you more details. This is extremely interesting. This transition here that happens at the level of the large deviation function was first found by Bodino and Derrida using MFT and predicted using hydrodynamic at the hydrodynamic level. And then with Sylvain Prolac, we were able to do the calculations using better ansatz and prove that it really occurs.
May I ask just
Of
some
course,
questions?
yeah.
So what is nu again? Sorry, nu is the asymmetry parameter, I suppose.
So here the asymmetry parameter, if it's big enough.
Right. But what is nu exactly? I mean, it's just, I forgot the definition, just the definition of it.
Oh, new.
Yes,
I understood nouveau.
No, sorry.
Okay. Nu is the asymmetry parameter.
Okay.
Yeah.
And so now, what is the order of this transition?
So you see, I don't know if it's easy to talk about orders.
Well,
So it's the derivative is
just derivative.
the derivative is
So that's,
discontinuous. Yeah.
So this one is okay.
Okay.
And then you say a shock, so that means that if you really look at the density
Profile.
you see,
So if you look at the density profile in this region, it's flat, and here it becomes shock-like. Yeah. So this is the work about the closed system.
But it's on a ring, right?
On a ring.
So
Yeah.
That's a function of J, right?
This is a function of J. Yeah.
So
Yeah.
when you look at the system, you have anyway some fixed J, right? When it's on the,
Yes.
so then, like, how do you see actually, like, what's the easiest way to see that there's a transition? Because that's if you measure the large deviation function, of course, you'll see that.
Yes.
But
Yes.
just like physically, of course, you'll just see some constant current, average current. Right?
Yes.
And
So
the density also is probably just.
yeah. So it's not easy to see. There are two ways. Either you just make your system run, and you select only those histories in which the current is anomalously big or small, but this is, as you know, exponentially rare. The other way, which is more useful, is to use, this is what now Chetrit and Touchet are working a lot on it, you, starting from the generator of the Markov, of the ASEP, you can write another Markov process in which the non-typical current becomes the steady state current. But then it automatically introduces some long-range interactions into the system.
We put some bias which kind of.
So in fact, you deform the Markov generator and you define a new Markov generator in which a non-typical current becomes a steady state current. But of course, it's not anymore the ASEP process. The naked, it's a conditional ASEP process in which you have effective long-range interactions. Okay? Yes, yes. And I have no good explanation for that. No, I don't know why. And I discussed with a few people, and nobody really, I mean, I didn't ask Derrida, I asked Thierry, and also Bertini, and people like that, and I have no good hand-waving explanation why it's there. Yeah. So you can now decide to simulate this deformed Markov process, and then you will see that the profile becomes non-flat. Yeah? No, but it is related to the Bose gas. It's a kind of Li 3/2. Body log, right. Body log, yeah. Okay, in this 5 seconds, I have 5 minutes. I will tell you, so in the open boundary case, the coordinate better ansatz does not work. So you have two solutions. Either you go to the matrix ansatz, I told you a bit about last week, and this is the technique to be used and to be generalized to compute fluctuations of current. Or more recently, some people have developed the so-called algebraic better ansatz, which is a more complicated version of the better ansatz to deal with open systems. So this is again a whole world which contains a lot of techniques and quite involved techniques. But I just want to tell you about two things. What was known in the 90s was the phase diagram of the open exclusion process using the matrix representation technique. So this was developed originally by Derrida et al. And then pursued further by many, many groups. And for example, these calculations involved some complicated polynomials and so on. And one of the persons which was the most active at the beginning of his career, I mean, Tomohiro, for example, computed the current in the open asymmetric exclusion process with any asymmetry rate. Remember that the original paper of Derrida, although I think they had written the general algebra, but they really focused on the ASEP case in which Q equal to 0 and playing with the algebra becomes much simpler. But Tomohiro in 1999 was able to compute the current, for example, here, using, so I forgot the name, Alshira polynomials? Ashke-Wilson? Alshira polynomials, and he got a very nice formula for this quantity, okay, which includes, I mean, a lot of very nice mathematics and combinatorics. If you want to learn more, look at this review paper of Bright and Evans, I think 5 years ago, in JFISE, standard paper on matrix techniques applied to exclusion processes. Okay, so I told you that. Another very nice result obtained by Derrida, Leibowitz, and Speer, which uses only the steady state measure, is that they were able to compute, for example, in the symmetric case, but also in the ASEP case, the density, the large deviation functional for the density profile. Here again, I mean, this is something which is worth talking about for a long time, but one very important thing is that it does not look at all as a local functional. It's a highly non-local functional of the density profile, and this is utterly different from the equilibrium case, where the density, the large deviation functional is really a very nice local functional of the density profile. So this is the equilibrium case, and this is a non-equilibrium case, which involves the solution of a nonlinear equation involving the profile you want to compute the large deviation at as an ingredient of your equation. So this is totally nonlinear. Okay, it's much more complicated. Another important point, all these things again deserve learning and discussing, is that this formula here by Derrida et al. Was obtained using the matrix ansatz. So they just took a profile and had to sum all configuration, micro configurations compatible with this profile. So in principle, we know how to do it. We have the steady state measure. We just have to sum things, but this is very difficult. But almost simultaneously, Giornalasigno, Bertini, Landim, Gabrielli, and Da Sole obtained this formula using MFT. Okay. They obtained it after, but this was the first connection between exact results and MFT, so this is important. Then you can ask yourself a similar question, but now for the current. What is the total current, the statistics of the total current transported in this open system? And as I told you, this involves not only the steady state measure, but also correlation at different times. So the knowledge of the matrix steady state solution is not enough. But more recently, with Alexandre Nazarescu, we were able to generalize the matrix product ansatz using an infinite number of tensor products akin to these multi-species models I told you about, and we were able to compute the generating function for the current, the large deviation function for the current. And again, the nice observation is that this H.K. Wilson function that Tomohiro got in the 90s appeared into the game. So some more things patched together. Okay, and you get a nice formula, a simple formula for the cumulant, for the current large deviation function. You see, it's not so horrible. After horrible calculation, you get a simple formula. And in fact, you can even get explicit formulas for finite systems, valid for any size, and so on and so on. Now I just want to finish, take maybe 5 more minutes to maybe patch with, can I? Yeah, patch with the infinite line ASEP. So this is mostly Tomohiro and collaborators' work, and other people in America, Corvin, Castell, and so on. Here again, if you take the infinite line, the basic formula comes ultimately from better ansatz. Okay, but you have to do more work. So the thing is that the green function, so the probability from going from an initial configuration to a final configuration, is known and can be written as a contour integral, which involves some of our permutations. And again, ultimately, one of the basic ingredients is the so-called Schutz-Tracy-Widom formula, which relies on better ansatz. Okay?
ZK,
they are again the momenta, but they are not quantified anymore. So there are no better equations anymore, because there is no quantification condition, there is no matching or rounding off of the thing. So now in principle, again, I mean, it seems simple to say, but very difficult to do. Knowing the green function, one should be able to trace out things and get information about observables. But this is very, very, very difficult. And again, one of the masters in this game is just sitting here, and you can ask him questions. So, for example, one thing which I found very nice and which has been done in the last 5 or 10 years, suppose we start with TASEP, with the step initial conditions. All particles are just in the negative side and nothing on the positive side, and particles jump with rate 1. And we want to compute the statistics of the total current which has flown through the first bound, Qt. Okay? Then, using the previous formula, in the TASEP case, it is possible to get a very nice expression for the probability that the total current up to time t is bigger than m. And this very nice formula is an exact formula. So I think probably this formula will please Gregory a lot, because this is by chance, or I mean more than by chance, this happens to be a typical formula that appears in random matrix theory. See,
T is actually
T is M here, sorry, yeah. I mean, there's M here. Yes, where is my M? Wow. T is here.
Yeah, I think it's M actually. The integral is actually.
So here is M.
Yes,
Yeah.
here's capital M.
And here M also? Yeah, probably. Or N on the left hand side, yeah. Yeah, sorry, I will. Of course, the M has to appear. So capital N is M, yeah? Probably, yeah. Yeah. So now you see this makes a connection between the world of ASEP and the world of random matrices, and different techniques can be used to extract the asymptotics. And here comes this Tracy-Widom and Panevet that Grigory told us about, and probably tomorrow will tell us about. Okay, so I think we are done. In fact, we are done. So okay, so this was very sketchy, but you see that different models require different techniques and connect to different parts of physics and combinatorics. And then there are many things that remain open. In particular, I didn't have time, sorry Sanjeev, to talk about the MFT. This was the last part. But all these results that I told you about the ASEP have been derived using hardcore combinatorics, probability theory, random matrix theory, or better than that. And of course, one would like to have another way, a more physical way, to obtain them. And a more physical approach is to try to write a hydrodynamic equations with noise for all these systems and try to extract from these hydrodynamic equations all the quantities that I told you about, maybe not exactly on the finite size level, but at least on the limit of large size systems. And this is a program which is partially in progress. So there are different works relating to it. And one, again, you should look at recent papers, review papers of Generalized in Reviews of Modern Physics, where they explain the MFT. There's a whole chapter about applications to ASEP, for examples, and so on and so on. So there are many works about that. I just want to finish by showing you a simple model, which is the Jamnowski-Leibowitz model, where you have the ASEP on a ring with a slow bound. This is a very simple model, and if the bound is slow enough, there is a phase transition which occurs, and this is quite simple to understand. There will be a blocking cluster here. But this is a very simple model, and nobody has been able to solve it. And many people have tried. So again, I think it's good that everybody tries to hit his head against this model during a few days or a few weeks. It can inspire some other development. Probably it's not solvable exactly, but it's a nice model to think about and to teach. So thank you, sorry for being late. Sorry for not being able to.
Snowbound, you mean at one location rate is much smaller?
Yes, I mean, then you have plenty of variants. Shikashi Arita recently wrote a paper on EPL where you can put 1/2, 1/3. You can put different rates. I mean, I imagine there has been dozens of papers inspired from this one. But this is the first paper, 92. And it's already a big puzzle. Yeah. Even I think 2 years ago, Leibowitz, Speer et al. Wrote a new paper on this very model, trying to get some more results. Probably Arvin knows more about it. And okay, I mean, it's an ongoing process. Okay, thank you very much.
We have time to take a few more.
I have a technical question on this. So you had this discontinued, like this phase transition for this current, right?
Yes.
What is the mathematical origin of this discontinuity? Some singularity in the.
So mathematically, you can again say it in different ways.
Okay.
Either you do better on that, and then there is this series that define the, in fact, that allow you to calculate this large deviation, cumulative generating function. And this is precisely the convergence radius of this series. Exactly. But this is not very insightful. More physically, and this is thanks to MFT, if you look at the MFT equations and solve them and impose that the current you want to observe, so this value of QT of t is given to J, so you put this as a constraint in the MFT equation as a Lagrange multiplier, and then solve the MFT equations with this constraint, you will see that you have time-independent solutions, so real steady state in this region, and the additivity principle applies. But when you cross this point, in this region, you have no steady state solutions anymore, and the optimal profiles in the MFT equations become time-dependent. So now you have solitons moving in your ring, but which depend on time. So there's a kind of global velocity. They become of the form some function of x minus vt, okay? And this is the reason that, so in fact, here, the time-independent solution become linearly unstable. The MFT equations develop a linear instability. So it's really a bifurcation in the sense of...
left-hand side depends on time, is it?
Yes.
Those are these dash
No, the dash thing are the solutions of the better equations for bigger and bigger systems.
Oh, okay.
So you should really think about the limit. Limit, which is the black. So it's
This is still time independent. Large division function on the left of still time independent.
the large deviation function is time independent, but the profile Q and P that optimize the action are time dependent. So mu of lambda is time independent, but Q and P depend on time.
It gives you the same.
It gives you the value of mu here.
Because you are asking for.
Yeah. So the optimal profiles are not anymore constant with time. No, it's not really linear. It appears linear in the picture, but it's not purely linear. No, you see, we are on very small scale here. It's -1. So of course it does not remain linear. You see, it's very small. No, it's not.
The other question? So I have a small question. So this MS finally, I mean, in principle, it's able to cover all the cases, all the different boundary conditions that you show?
Yes, but only in the weakly asymmetric case, because it has to be a driven diffusive system. Otherwise,
So
you don't know.
You would not be, not be able to reproduce the phase diagram of the ASEP with reservoir.
So strictly speaking, for example, if you talk about TASEP or ASEP with rates which are very different from 1/2, no. But a simple hydrodynamic reasoning anyway gives you the phase diagram. I mean, this phase diagram is mean fieldish. So just Berger's equation gives it to you. Okay? If you just use Berger's equation on an infinite system with rho plus and rho minus, you will just see that your step moves in one direction or the other direction. Krug did it in the early 90s. Yeah. So this is.
Here mu is the asymmetry.
Yes.
It's like Q.
Yes. In fact, why I call it nu, because you have to rescale nu over L. Q is 1 minus.
Oh, it's weak.
It's very weak asymmetry limit. Yeah.
And that's pi is included. Why is there a pi?
Where is a pi?
Afterwards. 2 pi, 4 pi.
Yes, because the radius of convergence of this series, it comes from Stirling, if you wish. Yeah. Yeah. Yes. So that you have 4 pi as a critical, or 8 pi. 4 pi as a critical value.
Okay. Let's thank you all again.